go. Hello and welcome back to Calculus 3, section 14.4, length of curves. So we would like to know how long is the path along our vector valued function r, right? We know that r will give us position, each individual point, right? As you go, time equals 1 second, time equals pi seconds, whatever. You can find locations. Then you can take your derivatives, find the velocity, find the speed, find acceleration. So all of that stuff is good. Now I would like to know how far would the bug, let's say, fly along the curve. And for that, we have length of curves. We are going to have 3 formulas for 3 different situations. Out of these 3, you already covered one. So in Calc 2, you learned that length of curve is given by integral a to b, square root, can anyone help me with this? 1 plus
dy dx squared.
Yes. The derivative, f prime of x squared dx. You can put dy dx, you can put f prime, you can put y prime, whatever you like. Great. So this is the way to calculate a length of curve on the 2-dimensional image. So to accompany this, we can just put some kind of a curve there. A, B, and then I'm just going to make this red and call that L. So to calculate length of curve, we are going to have this integral a to b. So that was in Calculus 2, and this formula is still useful because in some cases, right, you can get a trace by intersecting the shape with one of the planes, and then whatever trace you get would be a 2-dimensional function, so you can still use this to find the length of a trace. But we would like to move into the 3-dimensional space to operate, so now we're switching to Calc 3 because we want to go into 3D. Well, in order for us to, well, erase the 3D, don't put the 3D. First, we're going to do a 2D case because we need to convert this. So, which way we're going to deal with this? Well, we are first going to convert this formula. We're going to use dy dx squared. I'm simply going to multiply this formula by dt divided by dt. And that's going to fix our issues. Integral a to b, square root of, well, let's do another step. So dy over dx squared. And now I'm going to have dx dt and then dt. The next step is to bring this dx dt under the square root. And when you do that, it will pick up a square. And now you will multiply through, and you will get dx dt squared plus, and dx will cancel, and you will have dy dt squared dt. So what we just got here is the length of the curve for 2D in parametric form. You see dx dt plus dy dt squared dt. So this equation here is a 2D length of curve in parametric form. It's two-dimensional because we only have x and a y. Now we extend this into the one we want, which is a 3D one, because our bug is flying in a 3D space, having all of these curves, right? Whatever. If you take a look at this wire, right, this could be the path that the bug is taking as it flies through the air. Now this curve is described with the three vectors, xt, yt, zt. So I would like to have the length of curve with 3. Well, we just know to expand this by inserting z inside this formula. So L equals integral a to b square root of dx dt squared plus dy dt squared plus dz dt squared dt. This is equation we're after. This is our 3D length of curve, parametric form. That's the one you need. So now, how do we use this? Well, it's fairly simple, actually. You have your vector r of t given. What is that vector? Isn't that vector x of t, y of t, z of t? Right? These are derivatives, right? Okay. So r prime of t is dx dt, dy dt, dz dt. They're all squared and they have a square root. So what's that?
They cancel, it's just a velocity.
Yeah, that's the speed. It's the magnitude of the velocity. This integral from here can be simply recast as L equals integral a to b. Well, you can write it as this. It's the simplest way, simplest form to remember it. Because that's our equation. Now, does it make sense dimensionally? Of course it makes sense dimensionally because you are integrating velocity, right? You will get how far you went as accumulation of all the points that you passed through. So it makes sense. I mean, integral of speed. That's why I want integral of speed. So let's have an example. trying to find something that will not make universe explode. This might. Yeah, whatever, let's do it anyway. That's the spirit, right? So r of t is given as 2 cosine t, 2 root 3 cosine t, 4 sine t, for 0 to 2 pi. So we're looking for the pair. Go on. Did you all get 7? Because that would be wrong if you did. The answer is not 7. I found r prime, which is our velocity vector, then I found the magnitude of the velocity vector, and then I integrated that number real quick. And that's it. So that's the length of curve in 3D. Now, there's one more that we want to cover, and that's going to be, it's a good one, that's going to be the polar form. So we have Calculus 2 using Cartesian coordinates. Then we have parametrization, 2-dimensional, 3-dimensional. And now we are going back to polar form. If you remember polar from it was r theta. So for the polar form, we start with L equals integral a to b square root of dx dt squared plus dy dt squared dt. So this is our starting point. Now, we are going to rename t to theta. And I'm going to have also, since now I rename this, then the theta will stop. The theta will bring alpha and beta into the game as our end angles. So now I have alpha beta square root of dx d theta squared plus dy d theta squared d theta. So this is what we have. And remember that we need to have everything in terms of r and theta, not in terms of x, y, and theta. We do have those conversions, if you remember, where x is equal to r cosine theta. So, and r is a function of theta. So, technically x is equal to f of theta cosine theta. So if I want dx d theta, so I can replace it in here, then I have to differentiate this and use the product rule. So that will give me f of theta times sine theta with a negative in front plus f prime. I don't have room over here. So let's just do the blue calculation. So x equals r cosine theta, which is actually f of theta cosine theta. So that's my x value. So dx d theta is going to be derived as, so copy the first, f of theta times the derivative of the second, which is negative sine theta, plus f prime of theta cosine theta. And my y is given as r sine theta, which is f of theta sine theta. And when I find dy d theta, again the product rule, so f of theta cosine theta plus f prime of theta sine theta. So now plug in. So when we plug this in, we get L equals integral alpha to beta. And now I have to, oh, kill me now, I gotta square all of this. So square root of negative f of theta sine theta plus f prime of theta cosine theta squared plus f theta cosine theta plus f prime theta sine theta, everything squared d theta. Equals to now we have to square these. Square will kill a negative. The middle terms are going to cancel. I really don't want to write this. I can just write a lot of algebra and then just skip to the next step and write the formula. But then in life, sometimes you just write the things out, you know, like the very non-sincere apology letter. I don't ever know if you ever did those. I'm sorry I hurt your feelings. End. So square the first one plus 2 times, no, minus 2 times f prime sine theta cosine theta plus f prime squared cosine squared theta plus f squared cosine squared theta plus 2f prime sine theta cosine theta plus f prime squared sine squared theta, everything d theta. There we go. So these terms in the middle die. And now it simplifies beautifully. It's just you have to write all this. So if you take a look at the f squared terms, right, you can see that you can factor out f squared, so you have your square root. You can factor out f of x squared, and you have sine squared plus theta plus cosine squared theta. And then plus f prime of theta, not x, theta. F prime of theta, and you also have sine squared theta plus cosine squared theta. Isn't this amazing, the way it simplifies? So the whole thing collapses to integral alpha to beta of square root of f of theta squared plus f prime of theta squared d theta. So the formula we're after for polar form is L alpha beta square root of f squared theta plus f prime squared theta d theta. And that's the polar form. So let's calculate the length of the crust on the large pizza. What's the radius of the large pizza? 16 inches radius or diameter? Diameter is 16. So large pizza R equals 8 inches. So what's L? L crust. One slice. Well, we all know. What's the full circle? It's 2 pi r, right? Divide that by 8 because pizza has 8 slices. I mean, for you, it has 8 slices. For me, just one slice, just fold it in half and eat it. But for you, has 8 slices. So this is the L that we are after from 0 to pi over 4. Now, we can calculate this using the ancient Greek methods, which is circumference C is 2 pi r, which is 2 pi 8, which is 16 pi, and then divide that by 8 slices. So L would be 16 pi divided by 8 equals 2 pi. So the length would be about 6.28 inches. So we can do this using the Greek method. But why simple if we can complicate things and use Calculus 3? So we're going to calculate the length of curve as 0 to pi over 4, right? Because we want one slice. And then the radius of the pizza is 8. So we have square root of 8 squared plus the derivative of this is 0 squared d theta. That's integral 0 to pi over 4 of, this all cancels, so just 8 d theta, which is 8 times pi over 4, which is 2 pi. We knew this, but we can do it this way as well. In case you apply for a job at pizzeria, you can bring this up, right? That you can compute the length of the crust, because crust might be stuffed by cheese now that there is also, right? It's now it turns into a cost problem, and on the large volume, you might want to keep track of all of that. So that's the length of curves. We have 4 formulas altogether here, including, those 4 include the original Calculus 2 formula that still might be useful here and there, so keep that one in mind as well. So Calculus 2 formula, then 2-dimensional and 3-dimensional parametrization formula, and finally polar form formula, in case that, again, that one is also 2D. So we have 3 2D formulas and 1 3D formula for length of curves. Bye.